we are now happy to have Zoltan Bajnok, and he will tell us about Tracy-Widom distribution in super Young-Mills theories. Please.
Thank you very much. So let me start by thanking the organizers for the kind invitation and the opportunity to speak here. So I would like to report on result done in collaboration with Grisha Korchemsky and Bercel Bordish. They are both in the audience. So you could feel like in the optometrist probably now. You can cover one of your eyes and then you should tell me what is the coefficient of zeta 5 in the first column. If you can tell, then you are eligible to drive. So I'm presenting here 3 perturbative series. The first in QCD, in the strong coupling, running coupling. The second one is in the 2-dimensional O4 nonlinear sigma model, the free energy density. And the last one is a 4-point function in n equals 4 super Young-Mills. What is common in these 3 perturbative series that they contain zeta functions, even and odd, some of them only odd, and sometimes log2s. And the expression why I actually needed to shrink the later and the larger perturbative corrections was because they grow. They are bigger and bigger because they can contain all possible zeta functions up to a given transcendentality. Unfortunately, in QCD, we cannot calculate actually many terms. We have only these 4 terms, and probably we will have only these 4 terms for 10 more years. But if we evaluate the numerical value, we can see that they grow. So instead of doing the calculation in QCD, we would like to do the calculation in a similar theory, and the 2-dimensional O and sigma models are very similar to QCD in the sense that they have a dynamically generated mass, and they are asymptotically free in perturbation theory. So in this theory, because this is an integrable theory, we can actually calculate a lot of perturbative coefficients, and then we can see how they grow. And they grow like factorial. We can do the same in this n equals 4 super Young-Mills, and they also grow like factorial, and we expect that a similar factorial growth will appear also in QCD. So at the first part, I would like to teach you what you should do if you have a perturbative series which is factorially divergent. And I would like to explain, so there are basically 2 parts. The first is about the O4 model, when I introduce the ideas and the final solution. And then we will switch to this ADS-CFT correspondence and the specific observable, a specific 4-point function, when I would like to repeat the same. This is not complete in the n equals 4 case, but it's complete in the O4 model. So what is the O4 model? We already had a talk actually yesterday about this O4 model. It's a sigma model. Maybe it's related to the next talk in this sense. So it's almost like a free boson. Yeah, I try to use. So it's almost like a free boson, except the field is restricted on the unit sphere. Yeah. I'm not sure. Okay. So what we are going to do, so it's on the unit sphere in n dimensions, and it has an ON symmetry. And then we are going to couple a magnetic field, one of the constant charges, and then put this magnetic field very, very large, squashing the system in 2 dimensions, and then it's integrable and we can solve it. It's a quantum field theory, so I could take this Lagrangian and calculate the free energy density in perturbation theory. If I do so, I would use dimensional regularization. I have to renormalize the Baire coupling. I have to introduce the dynamically generated scale. And finally, I can write the free energy density in terms of a running coupling, which involves this dynamically generated scale and the magnetic field. And this running coupling very nicely resums all higher logarithms and log-log terms in the magnetic field. So this is a perturbative expansion based on the Lagrangian. One can do the calculation, 1 loop, 2 loop, 3 loop. We did it with Grisha some time ago. But of course, based on the Lagrangian, we couldn't go higher orders. But this theory is integrable. So using integrability, we could actually calculate, based on the method of Volin, Dima, Volin, we could calculate 20 terms, 40 terms, 50 terms analytically. Even better, if we do the calculation numerically, we could calculate 1,400 perturbative coefficients up to 4,000 digits. So I would like to teach you that having such an amount of data, you can extract a lot of physical information. In particular, you can extract non-perturbative corrections from this. So let's start with this observable. I know this observable, as I mentioned, 1,400 coefficients, and then, because I know it very precisely, I can really see that they grow like factorial. It's written explicitly here how they grow. Yes. Yes, okay. So they grow like this. So the first lesson I would like to teach you, and I would like to ask you to use your brain a little, so what can we do if we have a perturbative series which is factorially growing? It has a zero radius of convergence. So the idea is that I will replace with another series when I divide by this factorial growth. So instead of using this chi n as perturbative coefficient, I will divide by n factorial. I make another function. When I divided it, this is called the Borel function. So I'm making a transformation on this function. And this function behaves much nicer because it will have a finite radius of convergence. You can think of this transformation as evaluating the path integral in two steps. First, I evaluate the path integral when I fix the value of the action. And this is this Borel function. And then I integrate for all possible actions. So it's a very natural function. And then this basically shows you what is the inverse of that transformation. So I have to integrate that Borel function on the real positive line, and then I can get back my original function. Of course, if I would do it order by order, then I could get the same asymptotic series. So the idea is not to do it order by order, but to take this function, which is on the Borel plane, has a finite radius of convergence, and then do an analytic continuation in a clever way, such that then after the analytic continuation, I could integrate on the real line. Of course, if I have some singularity on the real line, then I got in trouble, but otherwise it's a good method. So to get some naive analytic continuation, I could just use the Paddy approximant. So I approximate this function by a rational fraction, and I fix this coefficient by comparing the perturbative expansion of the Borel function. Then I got a quite good, actually, analytic continuation. Doing in this particular observable I'm describing, I can realize from the zeros of the denominator of this analytic continuation that there is a cut starting at -1, and there is a pole at 1, and then a cut starting at 2. So this is a kind of typical behavior. And now when I would like to integrate on the real line, I see that there are singularities. So I have to do something. One way is to integrate a bit above, or otherwise I could integrate a bit below. So there is an ambiguity in the inverse of this transformation, and we can see what is this ambiguity. So what is the difference between integrating above and below? And I will see that the magnitude, for example, of this pole is e to the minus 2 over alpha. So it's non-perturbative. So this is one of the messages. If I have an asymptotic series, then necessarily I will have non-perturbative corrections. And then similarly, the cut will also contribute to this ambiguity. So the next slide explains a bit what we should do in general. And then I think it's kind of simple to follow, and I ask you to follow it because I think it gives a nice insight. So you have a function, a perturbative expansion, with factorially growing coefficient. We make this Borel transformation by dividing the factorial, and then we analyze this Borel function, and I'm to extract the analytic structure of this Borel function, it's enough to know the asymptotic behavior of your perturbative series. So if the asymptotic behavior, it looks like this, that we already divided by the n factorial, so the leading behavior is a constant, like p plus, say. And then if we could calculate the 1 over n correction and the 1 over n times n minus 1 correction, and let's assume I could calculate all of them and also suppress terms like 2 to the minus n times similar constant 1 over n times n minus 1, then I can easily resum by definition how this function was defined. I could make the resummation. And if I resum, for example, the constant term, it's a constant times t to the n, it's easy, it's 1 over 1 minus t. So it's a pole at 1. Similarly, if I resum this minus 1 to the m times p minus, then I will have a pole at minus 1. If I resum the 1 over n correction, it will give me a logarithm. If I resum the next one, it will give a term multiplying this logarithm with p minus, written here. So if I can calculate, if all these coefficients here, they will actually lead to the function which multiplies this logarithmic cut. So the function, the analytical structure of the function of the Borel plane is determined by the asymptotics. When I do this inverse transformation, integrating on the real line, then I will get some imaginary part of the function, and that imaginary part, that ambiguity, is completely determined in terms of the asymptotic behavior. So the non-perturbative corrections encoded into the asymptotic behavior of the perturbative series. So this is the message. Doing the calculation in our data, we had this 1,400 coefficient, we can actually could fix with very precisely this asymptotic coefficient. Once we fix the asymptotic coefficient so precisely, we could make the inverse Borel transform, and then we found an imaginary part, which was not expected from the result. So in order to have a real, well-defined result, we have to subtract this imaginary part. But the problem is that in this imaginary part, what we subtracted, and we calculated from the asymptotics here, then this is also a series which is asymptotics. So the final result was the perturbative part, and these exponentially suppressed corrections, what we calculated from the asymptotics, but they are also asymptotics, so we have to compensate also them. Borel resum them. Saying it differently, when we calculate the analytic structure, we found some logarithmic cuts, and the function multiplying these logarithmic cuts, but that functions also had logarithmic cuts. So we had the logarithm of the logarithm, so we have to compensate all of them, and there is this very nice theory of resurgence, how to do it. And if you do so, then, for example, out of this 1,400 coefficient, we could calculate the asymptotic behavior of the asymptotic coefficients, and we could compensate our original function, and we could compare the numerical solution of this free energy calculation, and we could see that we completely described the function up to the second non-perturbative order. So let me summarize what is the structural result for this free energy. We had the perturbative series. This perturbative series was asymptotics. Because it was asymptotics, there are non-perturbative corrections. From the asymptotical behavior, we calculated this non-perturbative correction. But because this is also asymptotics, there are higher non-perturbative corrections. So in principle, we believe that it's described by a trans series, a perturbative series, and many, many non-perturbative corrections, infinitely many, and each non-perturbative correction has actually a perturbative series, and they are related to each other in a very intrinsic way, such that the asymptotic behavior of this perturbative or higher perturbative series will determine higher non-perturbative corrections. So the question, is it possible to describe all these perturbative series and non-perturbative corrections? And the answer is yes. So in this ON model, we managed to actually find the basis of functions with which we could describe all non-perturbative corrections. Any higher correction could be described by some path, and then depending on the size of this path, if it were higher, then we got a higher order non-perturbative corrections. So this completed this theory in this ON model. And we would like to do something in n equals 4 super Young-ness. Of course, we would like to do it in QCD. But in QCD, we cannot do calculations. Even the Lagrangian of the standard model is filling an A4 page. So we will switch to the n equals 4 super Young-mills, which is just one line. It has 1 gauge bosons, 8 fermions, 6 scalars. Here we can also do perturbation theory. Of course, if it's just perturbation theory, it's not much better than QCD. What is nice about this theory, that this is actually integrable. So we have the gauge theory description, which is a conformal field theory. So we could calculate like 2-point function. We take this, say, complex combination of the scalar, and then we can calculate the 2-point function of this operator. This is the spectral problem, and we could expand it perturbatively. If we expand perturbatively, these are these red curves. Yeah, wrong. So here I'm presenting some observable, like a scaling dimension, expanded perturbatively from the gauge theory. Of course, it cannot go to very, very high coupling. But since we have this ADS-CFT correspondence that n equals 4 super Young-mills is dual to string theory, type 2B string theory on ADS5 cos S5, we could also expand the same observable, the energies of the spring states, in string theory. Then we will get a large coupling expansion, shown green here. This is also an expansion. And the conjecture is that these two theories are equivalent, but it's hard to compare these two expansions, actually. So the way we can prove, sort of, that this duality is valid, that behind this model, actually this is the Wirth string theory, is integrable. So we can use integrable techniques to calculate the spectrum exactly. This is done in terms of some thermodynamic Bethe-Ansatz equation or quantum spectral curve, and that provides this blue curve, which interpolates between the two, and by expanding in weak coupling or strong coupling, we can see they agree with string theory or gauge theory. So this is the spectral problem. Today, I would like to talk about another observable in n equals 4 super Young-mills, which is a 4-point function. So the 4-point function of half BPS operators. So the operators I would like to take like trace x to the k, and then these other two operators. And I would like to calculate this 4-point function. I would like to calculate this 4-point function in the limit when the size of these operators are large. I'm doing this because there are some perturbative correction which goes between the operators in this worksheet. They are connecting the operators, and if I'm sending this k to infinity, then I'm killing those perturbative diagrams which would connect the top, the face, I can cut this worksheet into two parts, a front octagon and the back octagon, and I'm killing those perturbative terms which wrap between these two, which connect these two. So this 4-point function in the limit when k goes to infinity it actually factorizes into the product of the same object, what is called the octagon. So I would like to calculate this octagon. Perturbatively, it can be calculated at weak coupling and can be written just as in terms of these ladder integrals. At strong coupling, we could calculate it by determining the minimal surface with the boundary condition of this operator, evaluating the minimal surface, and then summing up the small fluctuations. And of course, I would like to interpolate between these two with some integrable description. And the integrable description is that if I take just this one octagon, the front, if I cut half, the front picture, and I can cut it into two hexagons, and in the integrable description, I have to insert a complete system of states between this hexagon two-point function. I have to sum them up. And it's possible to do. The result is a determinant of an infinite matrix. The matrix element of this infinite matrix can be written in terms of this form. So this is it looks like a matrix element of the chi function between odd Bessel functions. So this is how this K and M is defined. And then the function in what appears in the octagon, it's written here. So it's some function of the cross ratios. We are in a conformal field theory. This is a very nice result. This is valid for any coupling, and it interpolates between the weak coupling result and the strong coupling result. What is interesting, that just slightly generalizing this expression, not to have only odd Bessel functions, but also even Bessel functions, one can actually introduce an integral kernel to understand this matrix element as the matrix element of the integral kernel between these Bessel functions. This is called the Bessel kernel. It's written here in terms of Bessel function, and multiplied with this chi, and this chi is called the symbol of this Bessel kernel. So what is kind of interesting and miraculous, I talked about only the octagon, but there are many, many observables which can be written exactly the same form, just with a different symbol function. For example, the Tracy-Widom distribution corresponds to the same Bessel kernel, where the symbol function is just the theta function, shown black here in the corner. The expectation value of the circular Wilson loop in n equals 4 super Young-Mills can be also written like this determinant, but the symbol is like 4 over x squared, and then also flux tube correlators, cusp anomalous dimensions, and even n equals 4 super Young-Mills theories, some free energy or Wilson loops can be written into the same infinite determinant form, but with a different symbol. So what we try to do, we try to develop a method to expand this determinant observable as strong coupling. You can think of these determinant observables as a generalization of this Tracy-Widom distribution from this hard cutoff to a smoother cutoff. So what we would like to do, we would like to make a strong coupling expansion. This is actually an interesting mathematical problem. And mathematicians started to solve this problem almost 100 years ago by Segő and Polya and Katz and other people. But recently there was a very nice breakthrough by Andrei Belitsky and Grisha Korchemsky. They could manage to calculate the perturbative correction, shown FLG here, in a very nice way. And the way they did, they introduced the resolvent, and they found a very nice differential equation this resolvent should satisfy. Combining this differential equation with another equation, how the resolvent was actually related to this observable f, more like the derivative of this f. They related in two different ways. We just came came up with some parameterization, and then this differential equation with this back coupling basically determined all these coefficients. So all perturbative coefficients can be determined in terms of moments of the symbol of the kernel. So this is a very general approach. It works for all determinants, all symbols. And then the strong coupling expansion explicitly written in terms of these moments of the symbol, written in this way here. What is interesting that the octagon at a special point y equals 0, psi equals 0 was actually related to the localization result by g minus g. Yeah, my time is up. So what we figured out recently, that how to extend this perturbative calculation to the non-perturbative level. So we could, from the perturbative coefficient, we had already many perturbative coefficients, we could calculate the non-perturbative coefficient. And the location of this non-perturbative coefficient was related to zeros of the kernel function. We calculated it explicitly, and we checked that we have a similar asymptotic relation between the perturbative coefficient and the non-perturbative correction. And we compared we checked numerically that this is really the right solution. So I hope I could convince you that if you have an asymptotic series, then necessarily you have non-perturbative corrections. You can actually calculate these non-perturbative corrections from the perturbative series. And then we use this machinery in one model, the O4 model. Actually, we solved it exactly. And then we started to solve also in this n equals 4 super Young-Mills. We don't have the complete solution yet. It's already interesting that we found this non-perturbative correction. It's very interesting to which this non-perturbative corrections belongs to, what is the interpretation, like worksheet and instantons. And it would be nice to investigate this question, generalize for other observables, and so on. So maybe I stop here. Thank you.
Questions?
I was going to ask about these worldsheet instantons. Do you have some idea of what they would be, how to construct them, or?
I don't. I don't, but there was one paper, I think, about this recently when they analyzed some integrated correlators, and then at the strong coupling expansion of the integrated correlators, they also found non-perturbative corrections, and then they went a bit beyond, then they investigated, but I haven't checked yet. Yeah, but there are some literature, and then we should follow this.
But do you expect to be able to explicitly construct solutions that correspond to this? Or
this would be very nice, actually, to explicitly construct the solutions, then compare the instanton action with the order of the non-perturbative correction, or even more, to analyze small fluctuations around the instanton, and it should give exactly the corrections we calculate.
At some point you had a picture of something that looked like lattice paths.
Like what?
Like lattice paths?
Yes.
Do they play
Yes,
some
yes,
role?
yes,
Could you comment a bit on that?
Yeah, sure.
Yeah, here.
So this was the generic solution for this full trans series in the O4 model. So I'm saying that this full trans series, the perturbative series, and then all non-perturbative correction can be described completely in this basic function, which I call A&M. We could calculate perturbatively this A&M function for any n to high orders. And then the final result can be interpreted like the perturbative coefficient. I'm just calculating one particular observable, which is called A11. Actually, it's the member of that basis, which is just connecting one to one. And then we found that the first non-perturbative correction can be described, say, this simpler path. So here, maybe I can show. Yes. Yeah. So, yeah, the simplest perturbative correction, maybe I just read. So it's A1 minus 2, A minus 2, 1. So this is the leading perturbative correction, okay? And then you can interpret as a path starting from 1, going to minus 2, and then back to 1. And the next perturbative, non-perturbative correction, it has two terms. You go from 1 to minus 2, 1, and then also from 1 to minus 4, and so on. But in general, for a generic non-perturbative correction, you have to take a path which starts from 1 and arrives at 1 and goes through those points which are actually determined by the, in this Wiener-Hopf solution, by the kernel of the Wiener-Hopf function. So each path contributes to a non-perturbative correction. And then to which order it contributes, it's related to the length of the path. Yeah.
Yeah.
Thank you. So this determinant representation is suggestive of some free fermion representation, some spectral determinant perhaps. Is there a way to identify what would be the Hamiltonian in which those fermions are living?
I don't know, but I think this original derivation by Kostov, Petkova, and Serban, it's used a kind of fermionization of the calculation. Yeah. But in general, I don't know. So I would say maybe it's related to some localization. And then
I mean, this Tracy-Widom distribution arises in the statistics of largest eigenvalue of some matrix models, and I think there is some free fermion picture appearing there, so maybe it can be carried over to this system.
Yeah, so this Tracy-Widom I was referring to with the Bessel kernel, it's related to the Gauss ensemble in the eigenvalue distribution near the edge, indeed.
Yeah, right.
Yes. Yes, so you are saying that this determinant can be fermionized in this case, yes, and then I'm just telling you this octagon was also kind of fermionized, but I don't know about the other observables, but maybe they can be also fermionized. Maybe that would be a way actually to deriving observables in the same determinant form. So one message is if you can bring your observable into this determinant form, then this is the way to make an expansion. Yeah, non-perturbative expansion. Yeah.
Very well. Then, in view of time, let's thank Zoltan again.